This will be attempt number 2 at getting this recording going, and here's hoping that it works this time. I'm going to be solving problems using results of Gauss's law and electric fields in a conductor. So we're going to have a few big ideas that we're going to use on this. One of them is that the electric field inside a conductor in an electrostatic situation is zero. If it isn't, it should say if it isn't zero, the charges will quickly rearrange themselves to cancel the electric field and make it zero. Charges in a conductor are free to move around, and they're not moving in an electrostatic situation. And that must mean that there's no force acting on them, which means that the electric field is zero. So there are non-static situations. This is when you have a conductor in a circuit and the conductor happens to be carrying current. Okay, but that requires a closed circuit for one thing, and then some kind of an external agent like a battery or power supply that can continuously push or pull the charges through the conductor. And that's not what we're looking at in these examples. We're looking at static situations. A second idea is that the unbalanced charge on a conductor will reside entirely on its surface. This is based off of this idea. The electric field inside a conductor in a static situation is zero. If you imagine that this is some solid blob of something, a conductor, for instance, and we imagine making a Gaussian surface on the inside of this thing. And the Gaussian surface could be a little cylinder. It could be any kind of a shape. I just tried to draw a cylinder there. And if you imagine doing an integral for Gauss's law of E dot n hat, whoops, I did it again. I wrote it in the version that was in the textbook I learned this from, but this could also be written as, I actually taught out of that for a couple of years too, as E dot dA, and this is equal to the charge that's enclosed by that Gaussian surface divided by epsilon naught, which is a constant, and we'll actually start doing some calculations with this today. Now, because the electric field is zero, this has to be zero. Everywhere inside this conductor in the static situation, the electric field will be zero, which means this side of the equation is going to be zero. Well, if this side is zero, then this side must be zero. This is a non-zero constant of nature, and that must mean that the, whoops, that's supposed to be Q enclosed. The charge that's enclosed by the surface must be zero. And it would be zero no matter where we go inside this conductor, which means there's no loose charge or excess charge inside the conductor, and whatever charge it has, it's all on the outside of it. And so that's a key idea. Also, the electric field on the surface of a conductor in an electrostatic situation is perpendicular to the surface at any point. If it has a tangential electric field, that would be pushing charges around on the surface. So the electric field is perpendicular to the surface at every point, which means if you've got a weird curved shape, it's going to be pointing all sorts of different directions. But at any point, you could draw a tangent plane that just touches the surface there, and the electric field will be perpendicular to that tangent plane. And if you had a tangential electric field anywhere, E sub t, that would be pushing charges around on this surface, and that means you're not going to have a static situation. When you first set the thing up, apply some charge to this maybe. For a brief instant, there will be tangential electric fields, but it doesn't take very long before the thing settles down. A really tiny fraction of a second, before it settles down and you're in a static situation. And once that's achieved, all of the electric fields are perpendicular to the surface. And then one fourth big idea is that when you get very close to the surface of any object, it will look like a flat plane. And if you go to the surface of the Earth, it appears to be a flat plane, especially if you're standing in the middle of Kansas or Nebraska. And the crucial point is that you have to be much closer to the object than whatever its radius of curvature happens to be. Even if you're 5 or 6 miles above the surface in an airplane, you look out the window and you can't tell that it's a curved surface. Sometimes you get that impression depending on the shape of the window you're looking through, but even at that height, you can't really detect the curvature of the Earth. So now the crucial point is you have to be much closer to the object than whatever its radius of curvature happens to be. Earth has a radius of curvature of about 4,000 miles. So if you're within a few miles of the surface of the Earth, that's pretty small compared to a 4,000 mile radius of curvature. It'll look flat. And if it's a smaller object, you just have to get closer. Okay, so those four big ideas we're going to need. And then some other ones that we'll need are the electric fields of some charge distributions of different shapes. If you have a spherically symmetric charge distribution that has a total charge Q, the electric field is going to be K sub E Q over R squared, or since K sub E is 1 over 4 pi epsilon naught, you could also write it 1 over 4 pi epsilon naught Q over R squared. And so that's for that type of charge distribution. If you have an infinite uniform line charge that has a charge per unit length lambda, the electric field is going to be, you could write it as lambda over 2 pi epsilon naught r, or 1 over 2 pi epsilon naught times lambda over r, or if you multiplied the top and the bottom of this expression by 2, you'd have 2 over 4 pi epsilon naught, and that 1 over the 4 pi epsilon naught, or 2 over 4 pi epsilon naught, is actually 2k sub e. So you could write it also as 2k sub e lambda over r, but we'll have use of this particular relation in one or two of the problems as well. Then, if you have an infinite sheet of charge or plane that's conducting, the electric field is going to be sigma over epsilon naught, where sigma is the charge per unit area. Again, it doesn't really have to be infinite. Any flat surface, as long as you get close enough to it, can look like an infinite plane. And so the electric field would be this value. If you have an infinite plane of charge that is non-conducting, the electric field above that is sigma over 2 epsilon naught. So it's 1/2 of the value that you have here. And those are the things that we're going to be making use of. So let's try some problems out. Very first problem, what is the approximate field strength 1 centimeters above an ordinary sheet of paper carrying a uniform surface charge density of sigma equals 45 nanocoulombs per centimeter squared? All right, well, an ordinary sheet of paper would have a length of about 28 centimeters and a width of about 21.5 centimeters. And so if you're 1 centimeter above it, that's pretty close to the surface. It won't exactly look like an infinite conducting sheet, but it says the approximate field strength. And so we can use the expression. In this case, it's not a conductor, so we can use the expression for an infinite plane of charge to solve this, and it would be sigma over 2 epsilon naught. So for this one, oops, that is not the problem I wanted there. Our electric field, sigma over 2 epsilon naught, and sigma in this case 45 times 10 to the minus 9th coulombs per meter squared. And I just replaced nano with times 10 to the minus 9th, 2 epsilon naught. This may be our first glimpse of epsilon naught, this fundamental constant of nature. 2 times 8.85 times 10 to the minus 12th. And the units on that are coulombs squared per Newton meter squared. And the reason that we know that those are the units is because when we were using our K sub E, which is 8.99 times 10 to the 9th Newton meters squared per coulomb squared. Well, K sub E is equal to 1 over 4 pi epsilon naught. So if you solve this expression for epsilon naught, you'd be dividing by this, and you'd have these on the bottom, but that would give epsilon naught units that are the inverse of these, the reciprocal of these. So that's why it has that. Anyway, in this case, if you plug in all the numbers, you get that the electric field, we're lucky to have, actually, the electric field does not depend on the distance above the thing. If you've got an infinite sheet of charge, which this is not, but if you have an infinite sheet of charge, this doesn't depend on the distance away from the sheet. So we can claim 2 significant figures if we're going in the center of the thing, and we'd get about 2.5 times 10 to the 3rd newtons per coulomb, which isn't a super strong electric field, but it's just a sheet of paper. So that's how that thing works out. And as far as the units go, if you kept track of them, you'd have coulombs per meter squared divided by coulombs squared per Newton meter squared. You flip that and multiply, and you'll have Newton meters squared per coulomb squared. So that's out of there. Cross out those. Coulombs over coulomb squared just gives you a coulomb left on the bottom, and you end up with newtons per coulomb, which is are the units we've been using for the electric field. So that's how that one came out. And it's an approximation, but you can do things like that once in a while. And so that's about what the electric field strength would be. The trick would be managing to get a uniform surface charge density on a sheet of paper. That could be challenging. Okay, now we've got something here. What is the electric field strength just outside the surface of a conducting sphere carrying a surface charge density of 1.4 microcoulombs per square meter? All right, well, when we were looking at a spherically symmetric charge distribution, we thought that it would be 1 over 4 pi epsilon naught q over r squared, where q is the total charge on the thing. But in this case, it doesn't tell us what the radius of the thing is. We'd be just outside the surface, so if we knew the radius, we could do that. Without the radius, we don't know what the surface area of it is. All we know is that it has a surface charge density of that, and that would be sigma in this case. Surface charge density 1.4 times 10 to the minus 6, that's what micro means, coulombs per square meter. Okay. However, we're going to use one of those big ideas we had, big idea number 4. When you get very close to the surface of any object, it will look like a flat plane, like the surface of the Earth looks in Nebraska or Kansas. And the crucial point is we just have to be much closer to the object than the radius of curvature. So it's going to look like a flat plane. That means It's a conducting sphere, so we can think of it as an infinite plane of charge, and in that case, the electric field is just sigma over epsilon naught. So let's do the calculation for this thing. E will equal sigma over epsilon naught. Just plug in the numbers. 1.4 times 10 to the minus 6th coulombs per meter squared. And epsilon naught again, 8.85 times 10 to the minus 12th coulombs squared per Newton meter squared. And just plug in, I just did the dimensional analysis on those units there and showed you that it would end up being a Newton per Coulomb. And in this case, the electric field, you can check this, but it would be 1.6 times 10 to the 5th Newtons per Coulomb. On the other one, we had, let's see, 2.5 times 10 to the 3rd Newtons per Coulomb, which is just about 100 times smaller than this. And I can't remember what the dielectric strength of air happens to be, but this may be getting close to it. I'm not positive about that. I'll have to look that up later. That's if you make an electric field strong enough, it will overcome the ability of air to be an insulator. And what it does is if the electric field points that way, the electrons and the atoms will be pulled that way, and then the protons get pushed that way. But you can shred the electrons off of the atoms in that case. And then you've got a plasma. You have negative charges that are now free to move in that direction and positive charges that are free to move in that direction. And that causes a spark or a bolt of lightning, depending on the quantity of things you have and just how strong the electric field happens to be. So there's another one. Okay, this one, let's see, we have a net charge of 5 microcoulombs is applied to one side of a solid metal sphere. Okay, solid metal sphere. That means if this is an electrostatic situation, there is no electric field inside that solid metal sphere. And after electrostatic equilibrium is reached, what are A, the volume charge density inside the sphere, and B, the surface charge density on the sphere? And this says, assume there are no other charges or conductors nearby. Okay, so let's worry about A and B first. Well, A, we said there's no electric field inside of a conductor in a static and electrostatic situation. And if there is no electric field, then any Gaussian surface you do on the inside of that thing, okay, if you integrate over a surface that is entirely within this sphere, you'd have E dot dA. This is going to have to be 0 because there's no electric field in there. And that means that within that Gaussian surface, there's going to be no charge. And so if there's no loose charge in there, then the volume charge density has to be 0. There's no charge, net charge inside the conductor. All of the atoms are neutral in there. So this is going to be sigma equals 0 inside. Actually, for volume charge densities, we often use the letter rho, I think, if I can remember right. I can't remember what your book uses for sure, but that would be the volume charge density. Okay, but then it asks the surface charge density on the sphere. Okay, well, we have 5 microcoulombs. It's spread over a surface of a metal sphere that's 2.0 centimeters in diameter or 1.0 meters or centimeters in radius. And so the area, surface area of this thing is going to be 4 pi r squared. That's the surface area of a sphere. Sigma, the surface charge density, will equal the amount of charge on it divided by 4 pi r squared, the area. And we have 5.0 times 10 to the minus 6 coulombs. And we have 4 times pi times 1.0 times 10 to the minus 2 meters. That's what a centimeter happens to be. And if the diameter is 2 centimeters, then the radius is one of those. And we have to square that. Okay. So we just have to plug in the numbers on this thing. And when I do it, I get to two significant figures, about 4.0 times 10 to the minus third coulombs per meter squared. And got coulombs on top, you'll have meters squared on the bottom. So that would be it. And you could write that as 4.0 millicoulombs per square meter if you wanted to. So that's it. Now, C. Which of your answer depends on the assumption that there are no charges or conductors nearby? Okay, well, if this is an electrostatic situation, there's always going to be no volume charge density inside. However, this is a metal sphere. That means it's a conductor. If it's only the charge that's on the sphere, it'll be nice and evenly distributed. But if you had a situation where we have the sphere sitting here, and then someone brought some big rod near this thing, and maybe this thing's made out of, maybe it's an insulating rod, but a large amount of, let's imagine that negative charge has been placed on this thing. And so it's all over the end of it and all over the sides of it, and it's just got a whole bunch of extra electrons on there. And if this is a non-conductor, they're not going to be moving around. They're just going to sit there wherever they happen to be. Now, initially, you had a bunch of positive charge on this thing that was just sort of evenly distributed, and maybe some fraction of the atoms on the surface were missing an electron, and that's what gave you this nice even surface charge density that's positive. However, if you bring a negatively charged object near there, that's going to drive more negative charges away from this side, and you'll have an even greater positive charge distribution on this side of it. And you might end up with those negative charges that were driven away actually neutralizing the positive ions that were on this side, or maybe they at least diminish the amount of it, or they could even overcome it. And you might end up with this side being negatively charged and this side being positively charged, but more positively charged than that side is negatively charged, so that it still has a net charge of 5 microcoulombs on it. So if you bring some other charges up to this thing, you could foul things up. Similarly, okay, let's imagine that you didn't have this, but you had this thing that had a surface charge density on it that was positive, and then maybe you bring a cylinder up near this thing that is neutral, but it's metal. Okay. And so you bring that up there. Well, you've got these positive charges on here. Those would attract negative charges in this conductor here. And what you might end up with is a bunch of negative charges here and elsewhere on this conductor, you might have positive ions because those electrons, the negative charges, had to come from somewhere. And so there would be parts of this conductor that are actually positively charged if it was insulated from the outside world. But now these negative charges are going to attract more positive charges, and it's the same situation that you had here, where you'll end up with even more negative charges in this getting pushed to the other side. And so you'll end up with a charge imbalance. And so the surface charge density that we calculated here wouldn't be accurate anymore. It's not the same everywhere on the thing. Okay, that was complicated. Lots of things going on with that one. All right. Here we have yet another one here. We have a surface charge plus Q lies at the center of a spherical conducting shell that carries a net charge of Q, and we're not told the sign of this net charge, but let's just imagine that it's positive here for the time being, and maybe imagine that it's negative too. So yeah, we'll imagine it's positive, the chart to start with, and then maybe we'll try imagining what happens if it's negative. So positive Q at the center of a spherical conducting shell. Well, I'll give myself a little center thing here. So there's the center of it. That's where the charge positive Q is. And I'll draw a conducting shell here, but I'm going to intentionally make it probably thicker than it would have to be, but I'd like to consider the different parts of this conducting shell. So anyway, sitting here, I've got a charge plus Q. So maybe that's I don't know, an alpha particle. It's got a charge on it, but it's probably going to be some macroscopic object that has a bunch of charge on it. So we have that. And what's going to happen if you stick that charge in there? Now, remember, there was already a charge plus Q that was on this charge, on this thing, that would have been distributed around the outside of the surface. Now, this is the inside of a conductor. The shell of this is conducting. So it's the inside of the conducting shell. It's a conductor. It's an electrostatic situation. The electric field is going to be negative or zero in here. Excuse me. It's going to be zero. And if I were to take a Gaussian surface that surrounded the inner wall of this thing, okay, so I'm just drawing a dashed line to represent a Gaussian surface, and I can imagine integrating over this Gaussian surface, and Gauss's law says this: if you integrate over a closed surface, E dot dA, that will equal the charge enclosed divided by epsilon naught. Okay, but this is a conductor. Its electric field inside it will be zero. And so this side's going to be zero, which means that the charge enclosed has to be zero. But I know that there's a charge plus Q at the very center of this thing. How can that be? Well, there would be an induced charge on the inside surface of this thing that'll have a cumulative value of minus Q. And so that's what happens. And we don't know what the radius of this thing happens to be or anything else, but we do know that the net negative charge that's going to be on here is going to exactly cancel this charge out. so that the electric field inside this conducting surface is going to be 0. All right. Now, where did those negative charges come from? They came from the outer surface of this shell, which already had a charge of plus Q on it. We made that up, kind of. And if it had a charge of plus Q on it, now, after subtracting a charge minus Q from it, the outer surface is going to have a net charge of 2Q. So outer net charge of plus 2Q. Ooh, boy. Okay, so that's what we happen to have in that case. Now, it's sketch the field lines both inside and outside the shell using 8 field lines to represent the charge of magnitude Q. Well, I'm going to get a new piece of paper to do that because I don't really have room on this one to do it. Okay, so I'll make a bigger circle here too. And it said that we use 8 field lines if we have a charge of Q to represent the strength of that electric field. Okay, so here we've got a charge Q, okay, plus Q there, and supposed to have 8 electric field lines pointing away from this thing. So there's 2 of those field lines. Yeah, and I'll just, I don't know, have them look like this. And a way to kind of illustrate the strength of an electric field is to have more field lines, or where the field lines are the most crowded is where the electric field is strongest, and it's the strongest right close to that thing. So that's what we have inside. But on the outside, we've got a charge 2Q of it, and so we'll have to have twice as many field lines out there. And so remember, inside that shell, we don't have anything, excuse me. And I'll be putting arrows on all of these things. But if when we have a charge of Q, we have 8 field lines. When we have a charge of 2Q, we're going to need 16 field lines. So I have to double all of these things up on the outside. And it's going to drive me nuts, I think, but try to make it work here. Okay, I've just added 4 more. I have to add another 2 pairs of them. And I think this will be symmetric. I hope approximately at least as symmetric as I'm going to make it. So anyway, that's what we've got. Outside, we've got the electric field of a spherically symmetric charge distribution that is due to a charge of 2Q. Anyway, but we're farther away from it, so there isn't any place where it's actually twice as strong, because we're even out here, we're farther away. Okay, I'm going to let you try to imagine, and maybe we can talk about this sometime. What if it's a negative net charge, a charge minus Q on the conducting shell before you stick that plus Q in there, and see if you can reason through what's going to happen in that case. So that, let's see, we're starting to run out of problems here, I guess. Not quite yet, I think. Yeah, we're only halfway through maybe. Yes, we are. Okay. Well, that's all right. Just keep going. Now, consider an imaginary cylinder with a radius r equal to 0.250 meters and a length L of that. And it has an infinite line charge of positive charge running along its axis. So I'm going to draw that line charge first and just draw it at some weird angle here. And then imagine here that we've got this imaginary surface or cylinder that surrounds this thing and shares an axis with it. Let's see. This thing has a radius of 0.250 meters and a length of 0.400 meters. And the charge per unit length on the line is lambda equals 6.00 microcoulombs per meter. I think we're going to need the electric field of an infinite line of charge, which I had around here once. Too many sheets of paper going here. There it is. All right. My infinite line of charge, the electric field of such a thing is, we could write it 1 over 2 pi epsilon naught lambda over r. Lambda is the charge per unit length that they gave us here, or you can write it as 2 k sub e lambda divided by r. Okay, but what's the question? No, what is the electric flux through the cylinder due to this infinite line of charge? Well, I probably forgot to mention this, but when Gauss's law says the integral of E dot dA, that is actually the flux of the electric field through the closed surface. Okay, and so that's what we need to calculate, except for this infinite line of charge. What that turns out to be is this 2 k sub e lambda over r. This, let's see. Well, that's the actual value of the electric field, excuse me. This will end up equaling the charge that's enclosed divided by epsilon naught. So the net flux through this surface is going to be how much charge is enclosed by it divided by epsilon naught. So we can actually bypass considering this in this case and just talk about doing that. So how much charge is going to be enclosed by this? Well, the cylinder has a length of 0.400 meters, and the charge that's enclosed in this case is just going to be L times lambda, the length of the cylinder times the charge per unit length that's enclosing it. So 0.400 meters. I don't have to do a whole lot of calculation on this thing, times 6.00 times 10 to the minus 6th coulombs per meter. Oh, wait, it was asking what the flux is. Yeah. Oh, I'm figuring out the charge enclosed. All right. There we go. And now what did I do with my solutions? I threw them away. It's just going to be, oh, the flux of the electric field will equal lambda L over epsilon naught. So we plug in lambda, plug in L, or plug in L, plug in lambda, divide by epsilon naught. I guess I should write all of those things down. 6.00 times 10 to the minus 6th coulombs per meter divided by 0.400 meters and multiplied by, and divide that by good old epsilon naught. Hope you're getting used to this number. 8.85 times 10 to the minus 12th. Oh, let's see, coulombs squared per Newton meter squared. And this one, the units are somewhat challenging. You've got coulombs on top that you'll end up with, divided by coulombs squared per Newton meter squared. And what you actually get unit-wise when you get done playing with those is a Newton per coulomb times a meter squared. These are the units of electric field. These are the units of area. And electric field times area is the flux of the electric field. And in this case, it ends up equaling 6.78 times 10 to the 5th newtons per coulomb meter squared. Okay, so that's for part A. For part B, it says, what's the flux through the cylinder if its radius is increased to R equals 0.500 meters? Well, nowhere in this calculation did we use the radius of this thing. You can make it a whole lot bigger, but it's still, the cylinder is only, or bigger in diameter, but the cylinder only has a length L inside of it that has charge on it. And so that's not going to change anything. So for part B, the flux stays the same. You could just say it the same as A. Okay, so that's something that you can do. And then for part C, it says, what is the flux through the cylinder if its length is increased to L equals 0.800 meters? Well, originally it was 0.400 meters. If it's 0.800 meters, you'd actually double this value is all, because you'd have twice as much charge enclosed by the thing, and L is doubled, lambda stays the same, epsilon naught doesn't change. So you'd just double the value. So try to wrap your head around the way that we did that thing, and try to be comfortable with it. Okay, back to a sphere here. A solid copper sphere, this time of radius 15.0 centimeters, carries a charge of 40.0 nanocoulombs. Find the electric field A at 12 centimeters, B 17 centimeters, and C 75 centimeters from the center of the sphere. And explain how your answers would change if the sphere were hollow. All right, well, this is a solid copper sphere, radius 15 centimeters. At a point 12 centimeters from the center, you're still within the conducting sphere, and the electric field in a conductor is 0. So in an electrostatic situation, so A, you can just say that E equals 0 inside a conductor. And because 12 is less than 17 or 12 is less than 15, you're still inside of it. But for B, let's see, the electric field will just equal K sub E times the charge on the sphere, 40.0 nanocoulombs, divided by R squared, where R is the distance you are from the center of it. That's the R that shows up in this expression. So 8.99 times 10 to the 9th. Let's see, what do we got here? Newton meter squared per coulomb squared times 40.0 times 10 to the minus ninth coulombs, and then just divide by 17.0 times 10 to the minus 2 meters, because that's what a centimeter happens to be, and that has to be squared. And when you plug in all the numbers, you would get 1.24 times 10 to the fourth newtons per coulomb is the strength of that electric field. Let's see, for C, you just make the distance bigger. And so all you have to do is replace 17.0 times 10 to the minus 2 meters with 75.0 times 10 to the minus 2 meters. And E, and I'll say at 75.0 centimeters, is equal to 6.39 times 10 squared newtons per coulomb. So whereas this one's about 12,400, this one's only 639, and it makes sense. You've more than quadrupled the distance, and you'd expect this one would be less than a 16th of the value of that one, and that does happen to be the case. Then it asks, explain how your answers would change if the sphere were hollow. Well, if the sphere were hollow, you'd be inside a hollow space for part A, and there wouldn't be any charge inside your little Gaussian surface if you calculated it. There wouldn't be an electric field in there in that case. The charge all resides on the outer surface of the sphere. So answers B and C aren't going to change at all. You still have the same amount of charge on the thing, and nothing changes for that if the sphere were hollow. Still not so bad there either. Okay, a couple more. Here we have a solid metal sphere of radius little a, carries a total charge Q, and no other charges are nearby. The electric field, oh, I didn't, these came out kind of weird. Electric field just outside its surface is KQ over A squared radially outward. Is the electric field here also given by sigma over epsilon naught? By sigma over 2 epsilon naught? Well, first of all, it says it's a solid metal sphere. Now, this is going to be using that idea that if you get really close to a surface, it's going to look like a plane. But this would be a conducting plane, and this is the electric field of a conducting plane, or an infinite plane of charge. But if you get close enough to something, it'll look infinite. And so let's see if that happens to be the case. I wouldn't expect this to be right, because this is for a non-conducting plane. So like a infinite sheet of charge. And that's not what we have in this case. Maybe if it was a non-conducting sphere and it had a total charge Q on the surface of it, then this one might work. But that shouldn't work here. But here's what we can do. We know what the electric field is. It's KQ over A squared. So we have that. Well, let's rewrite K sub E here. K sub E is, just say, equal to 1 over 4 pi epsilon naught. And that's it. And then we still have the Q over A squared. And I'm going to redistribute some things here. I'm going to put a Q times, well, I'm going to group the 4 and the pi and the a squared underneath it. And then I still have a 1 over epsilon naught here. Well, what's Q divided by 4 pi a squared? 4 pi a squared is the surface area of the sphere. Q divided by that is the surface charge density, which is sigma. And so this expression is equal to sigma over epsilon naught. So now that's only true just outside or right on the surface of the sphere. As soon as you start moving away, it starts dropping off of that. But on the surface of the sphere, the electric field is the same as that for an infinite sheet of charge. So that one's kind of neat. All right, one last problem here. The electric field strength outside a charge distribution and 18 centimeters from its surface has a magnitude of 55.0 kilonewtons per coulomb. At 30 centimeters, the field strength is 33.0 kilonewtons per coulomb. Does the distribution have spherical symmetry or does it have linear cylindrical symmetry? Well, here's what's going to happen. If it's got spherical symmetry, then you'd be taking E of, let's see, I think I'll put the big one on top. E of 30 centimeters divided by E of 18 centimeters. And this is for spherical. This would equal some kind of Q divided by, or times K sub E times some kind of Q times, or divided by 30.0 centimeters squared. And you could replace the C with times 10 to the minus 2 meters if you wanted to, but it turns out they're going to divide out. And then at 18 centimeters, you'd have K sub E times Q divided by 18.0 centimeters squared. And if you play around with this fraction on the bottom, the K sub E Q's divide out, and you'd actually end up with 18 over 30 squared. Okay, and the units all divide out, and that'd be 3 significant figures on each of those, but that's the same as, let's see, 3 times 6 over 5 times 6, it'd be 3/5 squared, which is actually 9/25. Okay, now, if you had cylindrical or linear symmetry, you could do the same thing, but the electric fields look different in that case. And let's see, I've got a lambda over 2 pi epsilon naught r for those things. So for this one, this would still be E of 30 over E of 18. And I'd have lambda over 2 pi epsilon naught times 30 centimeters. And here I'd have lambda over 2 pi epsilon naught times 18 centimeters. And what you'd end up with is 18.0 centimeters over 30.0 centimeters, which ends up being 3/5. And that's good to 6 or 3 significant figures, as is that. Okay, well, which do we have? we actually know the electric field strength at 30 centimeters, and we know the electric field strength at 15 centimeters. So we can just divide them. E of 30 over E of 18 is equal to 55. No, 30 was 33 kilonewtons per meter, 33.0 kilonewtons per meter. And this other one is 55.0 kilonewtons per meter. The kilonewtons per meter divide out, and I've got 33/55, which is 3/5 to 3 significant figures. And so we have linear cylindrical symmetry in this situation for this charge distribution that we didn't know what it was. So that's stuff you can do just by playing around with some of these things. And I didn't have to do any real fancy calculation for this. I just had to sort of reason through it and see what it came out as. Okay, that's those things. And so I'm going to stop recording here.